Hey guys, have your notes here for 4-6 day 2. And what you're going to do is you're going to investigate what happens when you take a sine fraction and turn it upside down. So all that big long list of sine fractions that you looked at on that intro to graphing worksheet, what if you turned every single one of those fractions upside down and graphed those points? That would get you the graph of a cosecant, because cosecant is obtained by taking a sine fraction and turning it upside down. Same with cosine. You turn all your cosine fractions upside down to get secant, and you turn all your tangent fractions upside down to get cotangent. So I just want to show you, first of all, what the graph of cosecant, secant, and cotangent look like. They're kind of bizarre looking graphs. So the black parabola looking things consist of the graph of cosecant. And just like sine, this pattern goes on forever in both directions. Here's the graph of secant. Again, a bunch of parabola-looking things, and just like cosine, this pattern goes on forever in both directions. So, weird. Actually, these graphs look nothing like the sine and cosine graphs. But cotangent does kind of look similar to a tangent graph. So here's what tangent looks like, and here's what cotangent looks like. Very similar. You got to be careful with those. So let's back up. All the properties out here, yeah, you can copy them down, but I don't know. Yeah, I guess they're important, but I'm not going to quiz you over them. And even if I did, just draw the graph. Like, look at what one of the graph looks like, and then can you all tell me? Well, I think you can. I'm not even going to take the time to talk about it. Let me show you how this graph is obtained. So, the black parabola-looking things are the graph of cosecant. They're not technically parabolas because a parabola will go up and out forever. So like the domain of a parabola, what x's does it cover? You all always tell me for a parabola, the domain is all real numbers. It's going to get wider and wider and wider and wider and wider, and it'll eventually cover all real numbers. Well, that's not the case for these, so they're not true parabolas. This U shape is bounded by this asymptote and this asymptote. It will not cover all real numbers. It'll still continue to grow out and out and out and out, but just by such tiny increments because it's fenced in right here. It'll just keep getting closer and closer to the fence. Okay, now what I want you to focus on now is the orange sine curve that you see weaving our way through it. So check this out. Now remember, cosecant is just sine upside down. So, this orange graph is your sine curve. And let me show you how the little parabola-looking things are obtained from our sine curve. So, ready? Completely focus on the orange graph. Ignore the black ones. Completely focus on the orange graph. Looks like a sine graph. Starts at the origin, peaks at 1, touches down, valleys at -1, back to the x-axis. Every time sine has a y value of 0, ready? Turn that y value upside down. What do you get when you turn 0 upside down? It blows up. So every time sine, the orange graph, has a value of 0, when you turn it upside down to get cosecant, cosecant blows up and has an asymptote. Sine is 0, upside down, asymptote. Sine is 0, turn it upside down, asymptote. Every single time. Sine is 0, turn it upside down, asymptote. So every time sine is 0, you turn that upside down, it creates an asymptote for cosecant. Let's see, what is sine of pi over 2? Sine of pi over 2 is 1. So right here, there's a y value of 1. Sine of pi over 2 is 1. Turn 1 upside down. What do you get? 1. So this cosecant graph has a value of 1 right here. The sine graph has a value of 1. They share that point. Where my sine graph peaks, my cosecant parabola thing begins. Right here, sine is negative 1. Turn negative 1 upside down for cosecant, and you still get negative 1. So the black graph of cosecant and the orange graph of sine share this y value of negative 1. When sine peaks, this parabola starts. When sine valleys, that's where this parabola starts. And again, I'm going to call them parabolas, but they're not truly parabolas. Okay? And then real quick, I'm going to mention this. It's going to go over your heads for some of you, and for others, you're going to be like, oh, that's cool. I'm going to just grab some y values. Let's talk about these y values right here. Y value is 1. Decrease, decrease, decrease. Y value is 0. So y value is right around here, close to 1, like 9/10. Turn 9/10 upside down. What do you get? 10/9. Something a little higher than 1. When this orange fraction is turned upside down, it creates this black fraction. Pick numbers down here, super close to the x-axis. Pick a y value that's a teeny tiny fraction, like 1/50. Turn an orange 1/50 upside down. What do you get? 50. So the black y value is going to be like 50. That's why it takes on that I'm going to infinity shape. Okay, enough about that. Next one is secant. Again, look at the function weaving its way through there. That's cosine. Starts at 1, hits, valleys, hits again, peaks. It's cosine. So again, every time cosine peaks, your little parabola for your secant begins. Every time cosine valleys, your little parabola for secant begins. Since cosine peaks on the y-axis, you've got a little parabola-looking thing on the y-axis. Not the case for sine. Its little parabolas are in different locations because sine peaks at a different location than cosine does. But they just look like they're a little shifted from each other. The graphs look the same. If you took away the x and the y-axis, you couldn't tell which was which. They look the same. Okay, now, tangent. Some things to point out about tangent. One is, I'm going to do the asymptotes first. Notice that tangent blows up here, 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 and here. What are those values? Those are at negative 3 pi over 2, an x value of negative 3 pi over 2. Negative pi over 2, tangent blows up. 0. No. Pi over 2, tangent blows up. And 3 pi over 2, tangent blows up. All the over 2's, tangent blows up. Turn blow up upside down, what do you get? For cotangent, when you turn undefined upside down, you get 0. All these over 2 blow up, over 2 blow up, over 2 blow up, over 2 blow up, turn them upside down. Now, at all of the over 2's, I get a 0, a 0, a 0, and a 0. Similarly, look at the zeros of tangent. Let's see, where does that happen? Well, this is at 0. This is at negative pi, and this is at positive pi. Where is tangent 0? Pi, 0, and negative pi. Turn 0 upside down. What do you get? Negative pi, 0, and pi. Turn that upside down. Your cotangent is going to blow up at those locations. Positive pi, 0, negative pi, 2 pi. Everywhere tangent was 0, cotangent blows up. And one more thing. So because this one does cross at 0, this one's going to blow up at 0. Keep in your mind that your tangent does pass through the origin. Your cotangent does not pass through the origin. That's going to be super important. And you're flipping all those fractions upside down to get cotangent. It kind of flips upside down the value of the graph. For example, leading away from the origin, you see how these are going to be tiny fractions and these are going to be huge numbers. Leading away from the origin, my tiny fractions become huge numbers when I flip them upside down. And as I get close to pi over 2, my huge numbers turn into tiny fractions when I flip them upside down. Again, that last part might have just went over your head. That's okay. That's all right. Here are some things that I want you to memorize. So I'm going to show you the board. You might want to screenshot this. This is super important. This is what you have to memorize. And if you forget stuff beyond this, that's okay. You can figure that stuff out. If this is the basis, if this is the foundation of what you know, you can figure out just about anything. So, hang on. Let me write on the board a little bit, and then I'll give you a chance to screenshot it. Here's what you need to memorize. Your sine graph looks like this, and it goes from 0 to 2 pi. Lock it in. Your cosine graph looks like this, and it goes from 0 to 2 pi. Lock it in. Your tangent graph looks like this. Here are some things I want you to memorize about it. It goes from negative pi over 2 to positive pi over 2. Those are your asymptotes. Lock it in. Negative pi over 2 to positive pi over 2. Those are your asymptotes. It passes through the origin. See? Lock it in. It looks like a cubic. That's the shape of it. Lock it in. Now, what do you have to remember to get to cosecant? Not much. Make sure you pair cosecant with sine. Everywhere sine peaks, draw a little u. Everywhere sine valleys, draw a little u. Secant, what do you need to remember? Not much. Just pair it with cosine. Every time cosine peaks, draw a u. Valleys, draw a u. Cotangent, a little more to remember. Several things. One is, it looks like your tangent flipped. So it kind of looks like a negative cubic. It does not pass through the origin. This one passes through the origin. Cotangent does not pass through the origin. And everywhere tangent blows up, cotangent has a 0. And vice versa. Everywhere tangent has a 0, cotangent blows up. Okay? I'm going to step away. You can screenshot it. Those are the things you have to memorize. It might be a good idea to, after you have taken a screenshot, write that all down once or twice. That'll help lock it in your memory. Alrighty, now, for the examples, I don't really like the way that your notes are set up, and I'll probably do them differently next year, but the way the notes were set up is we graph them from scratch. So we look at it and we completely draw the graph from scratch. Well, that's fine, that's good, but the way that your homework is set up and your test and quizzes are set up, all these secant, and cotangent questions, they're all matching. on your test and quiz, you don't have to create a cosecant graph from scratch. You just have to be able to match which one is which, or pick one from a multiple choice set. So what I've done, maybe not the best thing, but what I've done is I've drawn all 4 graphs, but I've mixed them up. So maybe just kind of hang out with me and maybe not draw all of these. Just kind of pay attention as we go along and write some of the stuff that I'm writing on your paper. And hopefully that'll be enough to get you a plan on how to process and do these from now on. So here's what I'm going to do. Again, these don't go together. I'm going to go through this list of functions. We're going to list its amplitude, b-value, find the period, talk about any shifts, and then we'll do the same thing for our graphs. I'm going to go kind of fast because you should be pretty good about finding A and B and period and all that stuff. So, first of all, this is a cosecant graph, so it matches with sine. So as we look to see which one this might be, I'm going to keep a sine graph in my head because sine and cosecant go together. All right, amplitude is 1. No, just kidding. Amplitude is 3. The b value in front of x is 1. Therefore, the period is 2 pi over b, which is 2 pi. Good. Moving on. Let's just keep going. Keep doing it for every problem. Amplitude is 1. This is going to match up with a cosine graph. B is 2. Period is 2 pi over b. I got the period as pi. Next one. Amplitude is 1. Cosecant is going to go with sine. B is 4 this time. Period is 2 pi over 4, which is pi over 2. Last one, amplitude is 1, but there needs to be a vertical flip. B is 2, so period is 2 pi over 2, which is pi. Also, let's see, plus pi over 2. That means there's been a shift left. Pi over 2. Got all that? Woohoo! All right, let's do the same with the graphs. Let's go through each graph. Let's list the amplitude, the period, if it looks like a sine or cosine, if there's been any shifts. So here's what I want though. Don't focus on the little parabolas. Kind of don't even look at them. I'm going to weave a sine or a cosine graph through there. So I'm going to take out my orange highlighter and I'm going to weave a sine or cosine graph. I'm going to touch and touch. So it means I'm going to cross halfway between. So touch, cross, touch, cross, touch, cross. Here I go. I'm going to weave it in. There we go. Okay, so you're looking at the orange graph. Can you give me the amplitude for the orange graph? Don't look at the black graph, look at the orange graph. What's the amplitude? Good job, amplitude is 1. Don't give me the b value. You get the b value from the equation. Look at the graph. Give me the period of a graph. So from start to finish, where do you see one complete graph before it starts to repeat itself? Sine, cosine, I don't care. So maybe you see, oh look, it looks kind of like a sine graph. If I start here and end here, That is one complete sine cycle. I like it. So from here to here, how far was that? That was pi over 2. It only took from 0 to pi over 2 to get one complete cycle. So the period of this graph is pi over 2. And it looks kind of like a sine graph with no shifts. So maybe the orange graph looks like a sine with no shifts. Does it have to be a sine? No. It could be a cosine that starts here. Maybe it was a cosine that had been shifted right pi over 8. Maybe. Maybe. So that's why I put a sine question mark. All right, moving on. Next one. I'm going to weave in graph. Make it a little darker for you so you can see it. Okay. Amplitude. How high and low does it go? 1. What's the period of the graph? Find a good start and finish place to where you see one complete cycle of sine or cosine. So if you're looking for sine, you might see that it kind of starts here, maybe. So sine starts on the axis, up one axis, down one axis. Or here's what I like better. I see a cosine from mid-hump to mid-hump. So this mid-valley to mid-valley is a cosine. It looks like it's been flipped upside down, but I don't care. I don't care that it looks like it's been flipped upside down. I just want to identify how far was it from the start of a graph to the finish of a graph. So if from here to here is pi over 2, and from here to here is pi over 2, I think I can say the period of the orange graph is 1 pi. And the orange graph to me starts here. It would finish up here. It kind of looks like cosine without any shifting going on. So cosine maybe. Keep going. Next graph. Amplitude is 1. Oh, hang on. I got to draw it. Well, I think that's the same. From here to here, looks kind of like cosine. It could be a sine with a shift, but looks kind of like cosine. And the last one. There we go. Look at the orange graph, not the black parabolas. Amplitude is, oh golly, not 1. I think the amplitude is 3. Find something that you like, either a complete sine cycle or a complete cosine cycle. What's the period? Well, I like starting here. Period is 2 pi. Looks kind of like a sine graph. All right, let's match them up. Do you see amplitude is 1, amplitude is 1, this amplitude was 3. Do any of these have an amplitude of 3? Yes. So this amplitude was 3, the period was 2 pi, and the orange graph looked like a sine. Number 1, amplitude is 3, period is 2 pi. It should look like a sine because the black graph was cosecant. I like 1 and 4. So I believe this goes with graph 4. What else can we match up? Amplitude is 1, period is pi over 2 for number 1. Period is pi over 2, it kind of looks like sine. Period is pi over 2, it kind of looks like sine. Oh yeah. 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 That was graph 1. Okay. Now these two, I think, were the same. So I'm looking for something that had a period of pi. Check for number 2. Check for number 4. Oh, number 4, it was secant, so it would match up with cosine. All right. So it's not going to matter really either way, but I do need to point out how it works. So I can say that, let me think about this. I can say amplitude is 1, period is pi, and it should straight up look, the orange graph should straight up look like a cosine. That's this one. Orange graph straight up looks like a cosine. So I could say this is graph number 2, which means this one should be graph number 3. So it's kind of hard to see. Let me kind of run through this with you. Of course, the amplitude is 1. Check. That's easy. It should look like a cosine with a vertical flip. So imagine your cosine doesn't start at a peak. It starts at a valley. So a cosine with a vertical flip, and it's moved left pi over 2. So cosine with a vertical flip starts at a valley, and it's moved left pi over 2. Again, I'm looking at the orange graph, not the black parabolas. So the flip means it starts at a valley. The left pi over 2, it's been scooted over. So this graph matches. So this is graph number 3. Okay, let's look at cotangents and tangents real quick. Video's getting kind of long, but I'll try to run through this quickly. Amplitude is 1. B is 3. Oh my goodness, be careful. Cotangent. The period is going to be 1 pi over 3. Remember why? The little period formula to get the period of the graph is 1 pi over b, not 2 pi over b like sine and cosine. Next one, amplitude is 1, b is 1, thus the period is pi, and we need to go did I do that wrong? No, I didn't do that wrong. We need to go right pi over 4. Amplitude is 3. B is 1/2. Period is pi over 1/2, which equals 2 pi. And this one will be moved left, pi over 4, and up 1. Okay, so the up one should make things pretty easy, because instead of the middle point crossing on the x of the 3 points graphed, 1, 2, 3, instead of the middle one crossing on the x-axis, the middle one's going to be crossing at 1 up higher. So 1, 2, 3, that's not it. 1, 2, oh, I think that's it. 1, 2, 3, that's not it. So I think this one goes with the number 4. Let me check the period of the graph really quickly. So from asymptote to asymptote, how far is this? It's pi. The period is pi. It's been moved up 1, and it's been shifted. Yep. Which one was that? That was graph number 2. Okay. This one, number 3, the period is 2 pi. So do you see a cotangent graph where it takes a width of 2 pi to get in one swoosh? You see a graph that takes a distance of 2 pi. Not that one. We've already used that one. Yep. Period is 2 pi. That's graph number 1, 2, 3. Graph number 3. Okay. Ooh, we need to talk about a shift here. So on this one, the period is pi. It's been moved right pi over 4. Keep in mind, cotangent does the graph itself doesn't cross at the origin. The asymptote does. The asymptote for cotangent falls at the origin. So, do you see an asymptote that has been moved from the origin right pi over 4? I think it's graph number 1. Graph number 1, there used to be there used to be an asymptote at the origin, and it's been moved right pi over 4. The period is 1 pi. Period is 1 pi. I like it. It's graph number 1. And then number 1, period is pi over 3. That must be, we've used number 1, we've used number 2, that must be this one. Is the period of this graph pi over 3? It is. So this would be graph number 4. Okay? Again, if you just try to do this all in your head and you're insisting on not writing anything down, you're gonna struggle some. I encourage you to go through, write down amplitude, period, all that stuff, and then maybe do the same on the graph itself. Write down the amplitude, write down the period, see what you can match together. All right, sorry, long video, done.